Hey and welcome. Today we are diving into something pretty amazing, the invisible, instantaneous decision making that powers pretty much, well, everything digital. We're talking about combinational logic, the secret sauce, the lightning fast brain behind the tech you use every single second. I mean, really think about that for a moment. You tap an app on your phone and it opens instantly. There's no pause, no moment of reflection. How? The answer is in these special circuits that live completely, 100% in the present. And that's our first big idea, the totally unique, memoryless nature of these circuits. They couldn't care less about what happened a second ago or even a nanosecond ago. Their entire world, their whole reason for being, is what's happening right now. And this table really shows you the heart of the matter. Over on the left, you've got our hero for today, combinational logic. Its output depends only on the input it's getting this very instant. It has zero memory. None. On the right, that's sequential logic, a whole other story for another day, and it uses memory. Its decisions are based on what's happening now and what happened in the past. But for us, the key takeaway is this. Combinational logic is all about the now. So you might be wondering, if these circuits have no memory, how on earth do they do anything useful? Well, it's because they're built from this incredible set of digital tools. The best way to think about them is like specialized Lego bricks, each one designed to do a very specific and very important job. So let's start with a classic challenge. Imagine you've got 4 different Netflix streams coming into your device, but you can only watch one on your screen. You need a way to pick just one, and you need to do it instantly. How do you even start to build a circuit for that? Well, you'd reach for this tool, the multiplexer, or just MUX for short. And its job is simple. It's a data selector. The train switch analogy is perfect. You've got all these tracks, all this data coming in, but a control signal flips the switch and lets only one train, just one data signal, get through to the single output track.
And the process is just beautifully simple. You've got multiple streams of data showing up at the MUX. Then a separate control signal acts like a bouncer at a club, points to one input and says, you get to go through. And bam, a single chosen output comes out the other side. This is absolutely fundamental for routing information in almost every device you own.
All right, challenge number 2. Let's say you've got 8 different LEDs connected to a circuit, but you only want to turn on LED number 5. You don't want a separate switch for each one. You want to send a simple code, like the binary number for 5, and have just that one light up. For a job like that, you need a decoder. A decoder basically does the reverse of our train switch, the MUX. It takes a small compact input, like that binary code for 5, and it activates one and only one of its many output lines. It decodes an address to find the exact single destination. And now, let's flip that problem on its head. What if you have something like a keyboard with over 100 keys? You really don't want to have 100 separate wires running from the keyboard to your computer, right? You need a smarter way to see which key is being pressed and then turn that into a simple, efficient code. And that, my friends, is the job of the encoder. It's brilliant. It takes a whole bunch of input lines and squishes them down, compressing them into a much smaller number of outputs that represent a specific code. So when you press the G key, an encoder is what translates that one physical press into the compact binary code your computer actually understands. Okay, so we've got our core toolkit down, the MUX, the decoder, the encoder. Now, let's level up and look at the advanced gadgets. These are the specialized tools engineers pull out for very specific but super important jobs. First up, the transcoder. Think of it as a universal translator for data, converting info from one digital language, say BCD, into another, like for a 7-segment display. Then there's the parity check generator. This thing is like a data watchdog, always sniffing around to make sure your information hasn't been corrupted. And finally, the barrel shifter. This is a speed demon. It can take a whole chunk of data and shift or rotate all the bits in a single clock cycle, which is absolutely crucial for the high-speed math that makes things like video games possible. So we have our toolkit, right? But just like with Legos, you can build the same castle in a dozen different ways. And this is where the real art of engineering comes in. See, the best design isn't the one with the most pieces. It's the one with the smartest, most efficient design. Because this is the hard truth of electronics. The more stuff you cram into your circuit, the slower it's going to run, the more power it's going to suck up, which means it gets hotter, and of course, the more expensive it is to make. The goal is always, always elegant simplicity. So how do engineers chase that elegant simplicity? Well, one of the coolest tools they use is the Carnot map. No, don't let the name scare you. It's not some terrifying math thing. Just think of it like a visual puzzle, a special grid that lets engineers literally see the patterns in their logic so they can find the absolute simplest, most efficient way to build a circuit. It's basically a blueprint for digital perfection. And all of this brings us to the final and most important point. We've been talking about these really simple, memoryless building blocks, but when you put them together in clever, optimized ways, that's how you get the incredibly complex and powerful digital world that we all live in. So, why does any of this really matter to you? Because these basic ideas are everywhere. They're handling the data routing that makes the internet work. They're doing the data compression that lets you stream video. They're running error checks to keep your photos from getting corrupted. And they're performing the billions of arithmetic operations inside your processor right now. All of it is built on this foundation. So I'll leave you with this thought. These circuits are making billions of logical choices every single second, with absolutely zero memory of what came before. They only know what's true in this exact instant. What does that tell us about the unbelievable power of simple, clear rules to create something so incredibly complex? It's pretty amazing to think about.